This lecture will talk about the general purpose I/O pins on the Raspberry Pi, and we'll talk specifically about the pins that are multifunction pins that have a function that's dedicated to communication protocols with other devices or other chips or things like that. So a couple of these pins are for I2C communication protocol. Now, if you remember I2C, it's a serial communication protocol generally used between two chips or two devices that are relatively close that can share a clock. So this is a clocked asynchronous protocol. So the two devices have to be close enough that they can share the same clock. So typically on the same board or something like that, they got to be physically close. So I2C protocol, it's got two wires. There's SDA and SCL. SDA sends the data, is where the data gets sent and received, and SCL is where the clock gets sent. Now this is as opposed to the UART, which we were just talking about. UART in the last lecture. UART is not clocked. There's no clock in there, so they didn't have a clock wire or a clock pin. I2C does have a clock pin, which makes it a lot faster protocol, but it is restricted in distance because you have to be close enough that you can send a clock without much skew. Okay, so pin 3 is the SDA line, pin 5 is the SCL line. So they can be used for I2C communication. The idea is if you had several different, say, Raspberry Pis or other devices that had I2C, you connect all their SDA lines together and connect all their SCL lines together, and they could communicate using I2C protocol. Now, of course, you'd have to write the appropriate code, and we'll talk about that later, but you'd write some Python code that can communicate, can read I2C data, write I2C data, things like that, but it would do it through these two pins. Another communication protocol, very common, just like I2C, is SPI, Serial Parallel Interface. We talked about this, actually, in the context of the Arduino. And actually, Arduino uses this heavily for communicating between the board and the shields when you stack them. But this protocol basically involves four wires, at least four. First, you got the MOSI. So if you look at pin 19, that says SPI 0 MOSI. That's master out, slave in. Then pin 21, that's MISO, master in, slave out. So each one of those wires is directional, right? So master out, so say this device is the master, then the MOSI is the output and MISO is the input. And then S clock, that's pin 23, SCLK, that's the clock that all the devices would share. So in addition to that, though, there's also a chip enable. Now, chip enable is because with SPI, if you remember, there can be a master, there's a single master, it's talking to many slaves. But it can only talk to one slave at a time. So it needs to assert the chip enable for the particular slave that it's talking to let that slave know it is communicating, right? And that that slave should wake up and listen. So each slave has to have a chip enable associated with it that the master can pull down in order to wake them up and have them listen. So in this case, in this board, you get two chip enables, pins 24 and 26. So 24 is chip enable CE0 and 26 is CE1. And notice the N after the name, CE0N, CE1N, that's N is for negative, so it's negatively asserted, meaning you have to pull that wire down. So the Raspberry Pi will send that from 1 to 0 to let the client know, let the slave know that it is being communicated with. So the Raspberry Pi gives you two chip enable pins. You might need more, depending on how many SPI components are on your bus, how many slaves you have on your bus, because you need a chip enable for every single slave. But this gives you two, which is pretty good. I mean, I don't know how many you're going to need, depends on the application. So this is SPI. And SPI, yeah, you got the MOSI, MISO, S clock, and you got the two chip enables. And again, when you actually do this, when you actually use this protocol, you would be using a Python library for communication, which we'll talk about later. Thank you.